The easiest way to introduce flexibility is by simply creating the flexible parts inside atoms, and we can do this through the ViewFlex capability. At this stage we haven't created a flexible body outside, in other words in some other FEA software. We will simply create a new value using atoms. At this stage we will ignore these values and specify the material that we have. So we can start off with our material that we've selected from a list, and important now is to specify that we want to do a stress analysis. We will not be manually replacing anything, and I would like to see some of the advanced settings over here. A very important step is to specify the element size, because the element size is going to dictate into how many elements this part is going to be divided into. Now, knowing that this plate has a thickness of 5 centimeters or 50 millimeters, I think an element size of 20 is a little bit fine and will create a very dense mesh. Dense meshes do give me more accurate answers, but at this stage I'm not interested in highly accurate answers. I'm actually interested in a model that will run quite quickly. So for this I will specify the element size to be a little bit larger and actually match the thickness of 50 millimeters of our part. And I will allow the mesher to refine the mesh where needed, but it shouldn't go to smaller elements than 10 millimeters. For the rest it's not really that important, and I can click OK to generate this mesh. At this point it's really important to notice that larger values will speed up this process. If you're going to use the default or smaller values depending on the size of the model, this might take longer than as shown in this video. Important, however, is to make sure that this part that you've made flexible is indeed connected, because it needs the connection locations to generate interface points with this part. It now states that about 700 elements were created, and it gives us a few other steps as well, and the process was indeed complete. For some reason my element wasn't visible, but by rewinding the animation control I was able to see the part. Now at first glance it might look like the exact same part, but if I press Shift and S it moves to a wireframe mode, and now I can see the actual elements. Now as I said, this mesh is quite coarse and it might not be ideal for highly accurate stress values, but it's perfect for my purpose at this stage, for simply generating more accurate loads for exporting for design optimization. So now I can run the analysis, and I have created a little script that runs my analysis, and you might get this error. Now this is very important. Remember that in Atoms we normally build models without redundant constraints, meaning we don't need more than one hinge to rotate a door, whereas in reality when we have a flexible door we actually need normally 2 hinges. Now that is exactly what happened in this model. Because I had redundant constraints when I only had rigid bodies, I actually simplified some of the hinges to represent other types of connections so that it doesn't create these redundant constraints. Now when we replace these solids with flexible parts, those constraints aren't redundant anymore, and all of a sudden my spherical joint now needs to be replaced by the original revolute joint, which now makes this system more accurately represented. I, in similar fashion, had a sliding joint over there, and I can now represent that as a revolute joint as well, since my flexible bodies don't give me these redundant constraint options. Now we can attempt to analyze this model again, and again it still complains that a kinematic analysis is not the correct way to model this. Now this is simply because I had this set in a script. If you use the interactive method, you wouldn't have this problem, but in case you had to create a script and maybe you also used the kinematic method, I'll show you how to modify this. So in this case, I've specified a kinematic analysis in the beginning, which is now not necessary anymore, and I will switch to dynamic, and this should run my script. I'll just switch off updating the graphics, and this is quite useful because the simulation length can be extremely long, especially when it needs to update the graphics after every iteration point, because the method of updating graphics actually take a lot more time than actually solving the analysis. So do remember to switch off updating graphics when you find that solving these simulations do take a lot of time. With the updated graphics display switched off, the simulations run much quicker, so we can get to our results now and have a look at how our model responded. At this point we won't see stresses as yet, we will only see relative deformations of our parts, but when we go into the post-processor we will see the results. So we can go to the post-processor, create a new view if you have, or new page. If you already have other pages with some preset data up there, we can right click, load the animation, and switch our contour plots to show as von Mises stresses. Now if you don't see the von Mises stresses option, it means you do not have this durability option over here, and that's normally because it may be off by default. So just make sure that you have the durability plugin activated. Go through tools, the plugin manager, and you make sure that Adam's durability is indeed on. That makes this possible for us to look at the stress results in this environment. Now I'll just generate or set the minimum value to be 0, and let's say the maximum value can stay like that. That's not a lot, that's about 34 MPa. So let's have a look at our results. Now in this case I've used a lot of steps and there's a lot of information to be processed, so I'll just cancel that and skip a few frames just to have the animation play a little bit faster. It means the Adam's pre and post processor also needs to manipulate less data, and it seems a lot faster. So we can see some of the stresses in our system over there. Now this is not actually what we're after. We're actually after exporting the loads at those particular locations. So now we have finished adding flexibility in our system, and now we're going to move out to the next phase where we're going to reduce the mass by utilizing these exported loads.